Now let's talk about the concentration of particles upon dissolving. So when a compound dissolves to form a solution, it can break into more than one particle. In this case, you can calculate the molarity of each ion in solution, and you can calculate the total ion concentration in solution. And that's if they are like sodium sulfate and ionic compounds. Oftentimes, you can actually do the molarity of each particle and the total particle concentration. And so that's typically what we do, is actually particle concentration, because each ion is a particle, but we'll see that acetone is not an ion. It breaks, it dissolves, it goes into solution as whole molecules. And so particle is the more general term. For example, what is the concentration of each ion and the total? And we can use ion here because these are ions, but we'll use particles down below. And the total concentration of ions in a 1.0 molar sodium sulfate solution. Again, this is review, but useful to do for what's coming up. If we know that it's 1.0 molar sodium sulfate, we know that there's one sulfate, so the concentration of sulfate ions in here will be 1.0 molar sulfate. We know there are two sodiums, so you get twice as many or twice as high concentration of sodium ions. And you can see that if you look at the dissolving reaction, we know that sodium sulfate is an ionic compound, that it is soluble, it is a strong electrolyte, it breaks up 100% into sodium, or two sodiums, and a sulfate. So start with 1 molar, or 1 mole, say, per liter, end with 1, 2, 3 moles, or 3 molar, 3.0 molar ion concentration. And we're going to develop a term called I, which is the Van't Hoff I factor, I. And I is going to be the number of particles that a compound breaks up into. So I for sodium sulfate equals 3. Now let's talk about acetone. Acetone is a carbon, hydrogen, oxygen molecule that, and as such, it is a non-electrolyte, meaning that it does dissolve in water, it does become aqueous, but it does not break up into any ions. So acetone dissolves as whole molecules. So the concentration of particles in this solution is just 1.0 molarity. So it's 1.0 molarity acetone, it's 1.0 molarity particles. And we could also say for this one, it's 1.0 molarity molecules. And when it stays together, I equals 1. And that's true for non-electrolytes. If we were to look at the I factor for something else, it depends on how many ions it breaks up into. So all we've done is I equals 3, because there are 1, 2, 3 ions that it breaks up into when it dissolves. What's the concentration of particles in a 1.0 molar acetic acid solution? Well, acetic acid is a weak electrolyte. And weak electrolytes are dealt with almost exclusively in other courses, especially in terms of their concentrations. For now, what we can know is that for weak electrolytes, they break up less than 5% into ions. So we could say, and we don't usually do a Van Hoff factor unless we, for weak electrolytes, until we get to these later classes. But for now, what we can say is the concentration of particles will be a little higher than 1 molarity. And that those particles will be mostly whole molecules. Remember, for weak electrolytes, the dominant species is whole molecules, and then there will be a small percentage, sometimes a very small percentage, of ions. Now let's do this for sodium chloride. It says, and take into account the molarity of particles. 17.2 grams of sodium chloride in 491 milliliters of solution. Well, that one we've done before, and we showed that it was 0.599 molarity sodium chloride. Sodium chloride breaks up into 2 ions, and we can also say that I equals 2. Then multiply the molarity times 2 to get to the molarity of particles. .198, 1.20. And we can say particles. We can say 1.20 molar ions because they are all ions for this problem.